very shortly, we should say something about two students of Galileo. We chose that topic because it is useful for the school also. And these two students are Cavalieri Bonaventura Cavalieri and Torricelli. Cavalieri was using special principle that would enable him to calculate the volumes of many solids. And his principle was such that if you can compare two solids, I wrote it flat, that line by line you can compare this with this, this with this, equal length, and the same with cuts, spatial cuts, then the volumes are equal. And why this was so crucial? Because Galileo was making trials to check the fall of the rolling ball from the such inclined plane. And he was checking the intervals in equal intervals of time, 1, 2, 3, 4. At first he was measuring with his pulse, and it is written in the discorsi that it was first the pulse, then it was more exact. And when he just counted 1, 2, 3, this ball traveled 1, 4, 9, 16, and 1, 2, 3, 4, and 1, 4, 9, 16, 25. It was years that he did it, every time more exact. And finally he wrote, it is strange, but it seems that there is as many square of natural numbers as natural numbers. And started to compare infinite sets. And infinite sets were at first taken into discourse by Galileo, so that his students was free to say, as a mathematical principle, that he compares all the lines with all the lines. And it was a big step, because Archimedes didn't dare. He was treating the same, almost the same principle, but like we treat daily bread. It weighs the same when it is cut into slices or just in one, so to say, lump. Okay. And Cavalieri formulated with his principle for the first time this principle, that the integration, summing of x squared was x 3 divided by 3. So this is integral, because that letter was the usual way of writing S as a sum. Okay, what is the use of it in the school? I would say my colleague will show exact how to build. Oh, yes, these are these 3 shapes.
In the shapes is very important 3 numbers. One number is, of course, 1, square of 2, square of 3. And everyone can see this number in the shapes. One of these shapes is 1, the square of 2 is diagonal in square, and square of 3 diagonal in cube. But in Europe, we are using special paper. A4 is most popular. What is it? A4 paper. Of course, it's a normal piece of paper. But why this piece of paper is special? Because this square have special numbers 297 210 297 divided by 10 equal but this number the same. Not quite the same, but around the same. 1 square of 2 and square of 3. You can see, very simple, we can do third of cube. 3 shapes give us a cube. But every shapes we can count value of these shapes. Simple. Sum x multiplied by x dx little bit, and is 1 of 3 cube. What? This is not necessary. Sum x squared dx equal 1 of 3 x. This is volume of cube. It was student of Galileo Galileiho.
So you can see that this principle of Cavalieri was essential in building up the notion of an integral, because it was integrating the square cuts of such a pyramid, and 3 of such pyramids were giving a cube. So this was a breakthrough. If you read the Cavalieri Exercitationes Sex, it was the consideration of such shapes described mainly in Latin, because it was the English of 17th century was still Latin. So this principle of Cavalieri was by him generalized to 3rd powers, to 4th powers, 6 until 7. And it was later on, of course, Newton and Leibniz who generalized it for all powers of this quantity x. But the time of Galileo and Cavalieri and Torricelli was not our way of thinking about polynomials. Polynomials meant some expression, say alpha plus beta times x plus gamma times x squared plus maybe some letter z times x n, but all these magnitudes were of different name. So it was very difficult to describe how to add length to a number and then length to a plane, I would say, shape, and then plane shapes to which it was added a length, compare it with volume. Well, Vieta wrote the whole such volume to explain how to do this trick, to add magnitudes of different names. And that was the origin of the polynomial, wielomian in Polish. That meant that we add magnitudes of different nature. Well, that was a difficult way to do, and Cavalieri, so to say, broke some obstacle to making it all clear. Good. So this triptych of Cavalieri is such a figure composed of 3 such shapes, which is very easy to build using this, I would say, A4 paper, just fits as a topic to school. Easy topic, taken from the history. Well, Cavalieri had a younger colleague, that was Torricelli, who was trained by him in this method of, well, comparing with infinity, such infinite number of such indivisible. Good. Now there is a letter. Well, a letter from Galileo to Cavalieri that was stating, and it is all in such a small brochure that I left here with Jan Gunzaga. And Galileo wrote, well, I considered for 40 years the line who just I considered as an answer to the Prince of Florence what shape should be given to the Ruges. What shape is the best? And he started to think and thought that it is the line that is drawn by the point on the ridge of the circle. And I considered and I wanted to calculate the volume under this line. I would like to calculate the length of this line, but it was in vain. And in this letter, Galileo was very, so to say, sad that he couldn't do it. It was circle 38 or something like that. Then, in the year, much later, in the year 44, Torricelli was making his exercises, yes, as a student of Cavalieri, and he wrote a treatise about parabola with 20 demonstrations of the famous theorem of Archimedes, just to prove that Cavalieri principle was right, such an exercise. But by the end of it, when it was all printed, he discovered that the area under the cycloid was 3 circles. And he used this exact expression, not the measure of it, because there were no number as real numbers as we had. He said, area under the cycloid is 3 circles. And he added appendix to his treatise on parabola. And appendix, it is like appendicitis, you see, something that is added to. And in his appendix, it was very clearly written that hypothesis of Galileo was true, and the proofs are so easy that it are good for school. It is written there in this small addition, so I have not to tell all the details. And to add something to it, a remark, I will only mention that in his treatise, in this appendix, Torricelli wrote that Galileo used the very peculiar way to establish his hypothesis, mainly not having integral calculus. He just cut off paper the shapes of this area under the cycloid, and these 3 put it on the way, and hypothesis was 3 times circle, moving circles. But later on, he had better ways and said, well, I was mistaken, it is less. And he left it. And leaving it as it was, Torricelli took and proved his hypothesis that it was right. No, it is a long story then to tell, and I will just leave you like in suspense. I think that explaining of all these intricacies of language and mathematics, which is very elementary, is a good topic for a seminar.